So where we left off was to try to show that C is 1 to 1. I rewrote the data back up here, and I think actually the first thing to do is to point out that C is well defined, and then we'll look at showing C is 1 to 1. Remember that well defined usually means just that it is a function. In other words, that if x is equal to y, then c of x equals c of y. That means it passes the vertical line test, so it's a function. So to do that, here's our input and output for C over here. We just need to make sure that if you have two input words that are actually the same word, then the output will be identical as well. And now we already know that that's going to work whenever the only difference is reduction of things like P times P inverse, because we defined C to make sure that it obeys the homomorphism properties, but just by definition. So we do need to check, though, that C takes care of equivalences that come through the relations on the first group. So since PQ is equal to Q inverse, we need to make sure that C of PQ equals C of Q inverse, which I need to finish writing. But here it is. C of PQ, using our definitions, gives me Q to the negative 2 times Q. I apply C to P and then Q separately. But then, of course, that one of the negatives cancels, and I get Q inverse. And C of Q inverse is Q inverse, just because by definition it takes inverses to inverses, and it takes Q to Q. Then we check the second relation, C of dpf. So that is going to come out to be dq negative 2f by applying it separately to dp and f. And then now I'm in the second group here, and q to the negative 2 is equal to d inverse f d f inverse. So replacing q to the negative 2 with that lets me then cancel the d and the d inverse and the f inverse, and I'm left with just fd in the middle. And that is the image of fd using my c. So that's equal to C of FD, which is what I wanted. I wanted to make sure that C applied to DPF is the same as C applied to FD. So basically this gives you almost everything you need, well defined, and the inverse. That's because this C is a little bit special. To define the inverse, so now I'm going to get C is 1 to 1. The typical way of proving 1 to 1 is to say that if the output is equal, then the inputs are equal. In other words, the converse of the well-defined passing the horizontal line test as opposed to the vertical line test. But another way to do it is to show that it has a well-defined inverse function, a function that goes in the reverse of the original direction, and that when composed with the original gives you the identity. So this will turn out to be the easiest way to do it here, because I can just define C inverse to give me back those three letters, D, Q, and F. Because if I'm going C inverse, it's going in this direction from the second group to the first. It only needs to be defined on Q, D, and F. It doesn't need a P because there's no P in there. In other words, the p will never show up unless I put in q to the negative 2, in which case I could then replace it with a p on output. Well, define for now the inverse of c to be those outputs, and we just need to make sure that it is indeed a well-defined function. Let's see. Block those off. And for that, we can actually look above. For instance, I guess actually no. We need to do what we did before, but it will look very similar. Is what I mean to say. Well defined. We need to check it on q to the negative 2, and I want to make sure that that comes out to be d inverse f d and df inverse. So when I put in q to the negative 2, I get out a q to the negative 2. And looking up above, now I will have to rewrite some of these these relations. Q to the negative 2, if I multiply both sides by q to the inverse, will equal p. This is c inverse here. We're going from the second group to the first one. You could put that there if you want. C inverse goes that way. So that in the top group here, in the first one, p is equal to q to the negative 2. But it's also equal to, using the second relation, multiply on both sides by f inverse on the right and d inverse on the left. It's equal to d inverse f d f inverse, which is exactly what I get if I plug in d inverse f d inverse df inverse to c inverse. So I'll go ahead and write that. C inverse d inverse f d f inverse. So it's well defined. I only had to check one relation that time because C inverse is going the other direction, and it only has one relation in the input group. Then the last thing to check is that it is composes to be the identity. And that's super easy. C inverse of C is obviously going to be the identity because both of them, C and C inverse, are only going to need, well, let's see, first C inverse of C. This one is the easiest one actually, because the outputs of C are D, Q, and F. Whenever the output is D, Q, or F, C inverse of C will give back D, Q, or F. When the output is Q to the negative 2, C inverse of Q to the negative 2, which we just found, was equal to Q to the negative 2, which is equal to P. But that's the input of C. So it does equal the identity. We'll just draw it like this. And then finally, you do need to check that C of C inverse is equal to the identity as well. I'll squeeze it in here. That's a negative 1 at the end. Let's look at that. C inverse outputs D, Q, and F. This was the easy one. C of C inverse gives you back D, Q, or F immediately. So you don't have to even look at that extra P value. So together, those two show that we are well defined and 1-to-1.